Okay, so today I'm going to solve a question from Gig for Gigs, and this question is in a list called Microsoft's Most Asked Interview Question. And the question on Gigs for Gigs is called Connect Nodes at the Same Level. But there is an exactly the same question on LeetCode, which is called Populating next right pointer in each node. I've never done this question before, but I'm going to try to simulate like the real interview, uh, especially for the like whiteboard coding interview, because preparing, I'm studying this like for my final rounds interview with Microsoft like in next year February. So I'm going to try to like walk through this problem and pretending that like this is an actual like interview, so that I will be like more comfortable when I actually like do the final rounds interview. So let's go ahead and look at the question. So on LeetCode, that question is number 116, and it's called Populating next right pointer in each node. Next. And the question gave us a struct node which in this form. So nodes containing value, left, right, and next. Let me go ahead and like read the question. So you are given a perfect binary tree. So what is a perfect binary tree? Where all the leaves are on the same level, and every parent has two children. The binary tree have the following definition. So this is the definition that they give us. Populate each next pointer to point to its next right node. If there's no next right node, the next pointer should be set to null. Initially, all the next pointer are set to null. Okay, that makes sense. Follow up, you may use only constant extra space. Recursive approach is fine. You may assume implicit stack space does not count as extra space for this problem. Okay, let's look at the example. So one key hint is it is a perfect binary tree. So it's always good like to clarify this like with the interviewer, because like different book define perfect binary tree differently. I believe like according to what I have learned, I think perfect binary tree refer to the tree that have all of the, basically each node either have 2 children or have 0 children. So like in this case. What else? You are given a perfect binary tree, left, right, next. You may only use, okay. Alright, so, and this is the example. So they have like 1, 2, 3, 4, 5, 6, 7. Where all leaves are on the same level. Oh, and every parent have 2 children. Okay, every parent have 2 children. So perfect binary tree, according to lead code, it's saying that it's a type of binary tree where all leaves are on the same level. So I guess so this is not a perfect binary tree because this leaf is on level, let's say we start with level 0, level 1, and level 2. So this leaf, so this is a leaf node, this is also a leaf node, and they are in 2 different level 0, level 1, and level 2. Alright, now we understand what is a perfect binary tree, and the question is they want us to modify this next. So initially next is pointing to null. They want us to modify it to point to a node that is on the same level. So in this case, they want me to point this node to this node since they are on the same level, and 4 to 5, 5 to 6, and 6 to 7. Oh, so what should I do? I'm thinking of using a hash map to store the location. To store, yeah, basically to store each node corresponding to their level. So basically, my thought process is we traverse through this tree, and I think it's good to use let's see, left visit. I think it's good to use left visit right, which is, what's it called, pre-order, in order. This is in order, and the reason that we want to use in order is because we want to, so the idea is we want to record each node, like all of this node, into a dictionary. So the idea is we want to record one, no, our key is the level, so it's like 0, and then we record it to 1, and on level 1 record it 2 and 3 like this. And the reason that I want to use left, I mean in order, is because it's allow us like to record the leftmost nodes first instead of like the right nodes, because we don't want 3 to point to 2, we want 2 point to 3. That's why we traverse through left first. So in this case, if we traverse like with LVO or in order, we would have visit so we go left right here, so we go left. So let's do LVR, 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 LVR. Right, so we go left, go left, go left, visit. So now we get 4. So 4, and we know that this is like 3 level. We need some sort of value that pass down from the top. So in this case, we would be able to record. So once we hit the 4 here, we don't go anymore because we visit and then we go right. So now we record that at level 2, we found 4. and then we go up and then visit 2, and just at level 1 we found 2, and then we go right, we saw 5 right here. So we go right, and then we go left, visit right. So here at level 2 we found 5, and we go up here. Since we already visit right, we go up here, so now visit 1. So right there we know that at level 0 we found 1, and then we go right, so then we go left, and then we go left right here, but we can't because it is a lift node. Then visit and right, so now we figure out that at level 2 we found 6, and then we go up and then visit 3. We visit this one, so we know that 3 is on at level 1, and then we go right. So right here we found 7, and we go left, visit and right here, and we know that it's on level 2. So once we can like store this as a list, and this whole thing would be a dictionary, which is a hash map of Python. So we can like grab all the items. No, so this is key, this is value. So we can like traverse through all of the value, like list of the value, and then do like dot next and point it to another one like this, another one like this, another one like this. All right, problem solved. I hope. Yeah, so, and the last node is just null, so we just keep traversing respect to like the sign of the list -1, because like this we don't connect to anything, it's just 1. Could we do better? You may use only constant extra space. Constant extra space is tricky though. Like for me, sometimes I forgot to ask question. Is there any like trick part in here? I mean, I kind of clarify the question that I want to know, like what is perfect binary tree? Just try to understand the structure of it carefully, and maybe okay. Like the question that I might ask is like, can I modify the nodes? I think constant, by constant space they mean like constant value, like no matter how big the tree is, it's always a constant space. But if I modify the node like to add like level, I'm going to have a extra space right here, which is alt n. So let me redraw like the picture one more time. 1, 2, 3, 4, 5, 6, 7. Oh, I have an idea. You can use like recursion to do this. Like this problem going to help me to become like a good thinker on how to use like recursion. Let me grab my erasable pen. So instead of using a dictionary, what I can do is I use the concept of recursion. So as you can see here, so like on let's say like this level, like on this level, when it recurs, oh, that's why the hint is perfect binary tree. This one will if it is not a perfect binary tree. Let me think a little bit. Which one would I appreciate if it wasn't like a perfect binary tree? So if you do recursion, you can like connect this and then like connect this. Oh, this is well, how do we connect this? Yeah. Okay. I'm a little bit trip. Let's see. So yeah, I have problem like connecting this. With recursion, I'm able like to connect this with this, this with this, this with this. Okay, let's think like a simple version of this. Say that we have just this and this and this. So let's say we are on like this stack frame. So we want to check our left child and right child. So if there is a left child and right child, we want to connect them. And then we want to recurse on this, and we want to recurse on this. So let's say we have left child and right child. So since we have left child and right child, we want to connect this. Since it is a perfect binary tree, just need to have left child and right child. Yeah, the problem is I don't know how to connect this to. But let me think a little bit. I mean, I'm on the right track right now, I think. I mean, when we're on this frame, we can see this. Recursive approach is fine. You may assume implicit stack space does not count as extra space. So we are using recursive right now. We need some sort of way of like return the child. I think we need some sort of way like to return this child to the stack and this child to the stack. Oh, maybe we can access this and connect those. Yeah, we have an ability to do that, right? Yeah, we can like from here. Yeah. Yeah, we have information. Yeah, so we need to check. So first we need to connect this, and then this dude have to check this and connect to this one. And then like write this, and write this. And this dude have the same role. It's supposed. So this dude have the role of connecting this. Let me erase this. So this node have a responsibility to connect this, and this node also have a responsibility to connect this. And then this node has a responsibility to connect this, and this node has a responsibility to connect this. If we look on this one, this node has a responsibility to connect this, and also a responsibility to connect this. All right, this is a better idea, like very better. Proud of myself. Wait, is there any catch? I mean, this is a perfect binary tree, so every level needs to have a full nodes. Need to have every level need to have every single space fill. So I think this might work, but let's generate some pseudocodes and then we test all the codes. So okay, same idea. So let's say like right now we are on this stack. So one, like this is always true. Since it's a perfect binary tree, you require to have either 2 childs or 0 childs. So this guy have 2 child, this guy have 2 child, this guy have 0 child. So if you have children, connect left child with right child. Okay, that's one thing. So you're supposed to do this connection, and then if your left child has a child, if it have a child, it must has two child. So if your left child, so right now we are on this stack frame. So if your left child have a child, have childs, connect his connects his right child with okay, let's define some term right here so it's easy to like discuss. So let's say this is me, this is child, and this is like grandson, grandkids. So if you have children, connect left child with right child. So this note, if you, okay, let's change the, okay. If you have, so if you have one grandkid, it guarantees that you have more than one grandkid, if that makes sense. Because like every single spot, every single space need to be filled, like in a perfect binary tree. So if you have grandchilds, you need to connect, let's say this is 0, 1, 2, and 3 child. You need to connect your one grandchild with two grandchild. Then do a recursive call on your children. Okay, I think it works. Let's run through one example and see if this program works. Because at Microsoft they like to test, so just so you know. All right. Okay, so C1. I think the numbers doesn't matter. So initially we are on this level, and then so if you have children, connect left child with right child. That's what I'm doing. Oh, let's do dot dot. Let's do a fancy dot dot dot. So we do this, and if you have grandchild, so this is me, this is my child, this is my grands. If you have grandchilds, you need to connect child 1 So this is, oh, sorry. This is my great grandchild, so we only care about 2 level down. So we need to connect our grand 1 with grand 2. So we do this connection. So if you have grandchild, you need to connect your 1 grandchild with your 2 grandchild. So this child. So, and then do a recursive call on your children. So do a recursive call on this one first, and then doesn't matter though. Oh, it's matter. No, it doesn't matter in this case. Like when you use hash map, it's kind of matter. But this, I don't think it's matter. So do recursive call. Now we are on this frame. So me would be here, and then my child is right here, and my grand is right here. So same idea. So now we are on this stack frame. So connect left child with right child. So like this. And then if you have grandchild, so I have grandchild, I want to connect my grandchild 1, which is, so grandchild 0, 1, 2, 3 with 2 like this. And then do a recursive call on this one. And then I connect my 2 child. And then I connect my child. I do a recursive call on this. And oh, no, I ran into trouble right here. So who's going to connect this too? So this will connect this, and this will connect this. Oh my goodness. Yeah, now we don't know. What's this right here? Right, who's going to connect here? It's how far do we need to check, like from this, from my original me to down here. Here's now we're missing this link. This will be connected by this guy. Okay, so this is a good concept, but it seems like it doesn't work. But I have another idea. So since this is a perfect binary tree, you can represent them as a what? Oh. Yeah, let's just focus on this part right here. We can do like while loop. So I know this might still work. We might just need to do while we have more level. This might still work. I don't know. We'll see. Let's try it out. Alright, so let's do this node like this. Agree that. And then this node just like this. Like this. So basically we just connect everything. So we just connect. So we just traverse through our left child and then go right. So left child and then go right, and then connect this with right child, and then go left, and then do left child, and then we go right, keep go right, and then we connect, hit right child, then go left. So until our so basically while left child, so we update our so if this is not none, we still want to connect with child dot left. I think it should work. So that right here, right here is supposed to connect this and connect this. Yeah, I think I figured it out. Yeah, that's basically it. This will solve that problem. So like this node will connect this too. It's also connect this too. Yeah, so basically, like let's say our stack frame is right here. So what we want to do is basically just traverse through here, and then we check. So we look at our children and ask our children if he or she have any child, any like kids, and then we could go right. So right here. So this is our stack frame. So we go right here. We look at our child, and we look at our left child, and we say, hey, left child, do you have any kids? So if you have kids, we keep going to the right. And then it's the same thing with here. So we ask our grandsons, our granddaughter, do you have any kids? If you have any kids, we want to connect that. So yeah, that's about it. I think what else can we test? I don't think I will write a code in here. Okay, I will write a code on another paper. So this is a recursion. Like the idea is we need to modify this portion right here, like this portion. So we have like left child and right child. So we want to keep going right, and here is like keep going left. And while there are more child, we want to connect them. I think this is a medium level question. Give me a good time thinking about like coming up with a solution. Very good. Alright, let's write some code. I hope my phones have enough memory to record this portion. Let's try to make it quick. Okay, let's call it define main. What do I supposed to return though? Just return a head node. Okay. And let's say we have head right here. And let's define some recursion. So define recursion. Say nodes. So the idea is we want to call recursion and passing. Oh, we want to check if head is null first. So the idea is to return head no matter what. Yeah, but if head is not none, you want to call recursion and call head. Alright, sounds good. So first we need to check our child. So if we have a child, we want to connect two of them. So if node dot left is not none. So if node dot left is not none, we can guarantee that there is a node dot right because it's a perfect binary tree. So we can connect them. Node dot left dot next is equal to node dot right. Okay, and then we checking, we call to attempt. So we want to check if our left child have any children. So temp is equal to, let's do temp right and temp left. Temp right is equal to node dot right. Temp left is equal to node dot left. Right. So I think I should swap this, but whatever. So it's fine. So right here, like for left child, I want to go to the right. So it's kind of intuitive. Okay, so it's kind of intuitive. Just call temp 1 and temp 2. So let's say temp 1 is equal to node dot left dot right. Temp 2 is equal to node dot right dot left. So let's say that we are on like this stack, like this stack frame. So we what we're doing right here is node dot left, so left child, and then we look at right. So if this is exists, we want to connect temp 1, which is this node, to temp 2. So while temp 1 is not none, we want to one next with temp2, and then we want to update our temp1 is equal to. So after that, we want to traverse through the next right child, so we just dot right. So temp1 dot right, temp2 is equal to temp2, and temp2 we want to update it to the next left, which is this one. And then on this stack frame, we want call recursion on node dot left and call recursion on node dot right. Alright, let's test it to see if it works or not. Hopefully it will work. Alright, so let's say that right now we are on this frame, stack frame, so head, this is head, and head is not none. Since head is not none, we call recursion, so right here, jump right into here. So we check node dot left, which is this one, so it's not none. So since it's not none, we want to connect this node with the right child, so node dot left dot next here, and then we create a temporary stack pointer called temp1 and temp2 to represent this. So temp1 is basically node dot left dot right, so this is temp1, and temp2 is node dot right dot left, which is this. So and since they exist, so we want to connect them to here, which is on this line, temp1 dot next is equal to temp2. And then we update our temp1. So since temp1 is right here, we want to update temp1 to right here. So T1 right here, and T2 now is right here, because it's temp1 right here is temp1 dot right. So temp1 dot right is right here, and temp2 dot left is right here. And then we check temp1. So temp1 is not null, it's not none. We want to connect temp1 with temp2, so connect right here. And then we update our temp1 to temp1 dot right, so which is like now, right now. And we go back to while loop. Since temp1 is null, we break the loop, we break this while loop, and then we replace node dot left. So now our stack frame is right here, and then we go back up here. So and we do node dot left, so node dot left would be here, since our stack frame is right here. So since node dot left it's not null, it's going to connect node dot left with its sibling right here, and then I create an temp pointer. I point it to here, so T1, and oh, sorry. So temp1 is node, so here's node dot left dot right, so temp1 is right here, temp1 is right here, and temp2 is node dot right and then dot left, so temp2 is right here. Since temp1 is not null, so it's going to connect to temp2 right here, and then it update to another temp1, temp2, which is null, so let's break this loop, and it's called node dot left and node dot right, so we call node dot left, which is like this. So okay, let's do this. If this is stack frame, so it's going to, since node dot left it's not none, it's going to connect their children together, and then it's trying to look for current channel. There's no current channels, so just break the loop. Yes, so I think this will work. Yeah, already tested. Is there any edge cases? Not I mean, it's perfect binary tree. If the input is perfect binary tree, yeah, I'm sure that this should works. Let's already test this. Yeah, in the case that the head is none, it just return none. So perfect binary tree, the tree must be full, you know. So I guess this is it. I think I'm really like my performance, like the way my thought processes, and I think I'm getting more like organized, more thoughtful when I solve this problem, and hopefully I will be ready like soon. Like I have an interview in February next year, so hopefully I will be ready by then. Alright, thanks for watching, and maybe leave some comment to see if I make any mistake, if there's something I need to improve. I would love to hear that as well. Yeah, but for now I'll talk to you guys like in the next video. Alright, bye.